We are currently building machines that process information using the laws of subatomic physics. By utilizing quantum states like superposition, these systems can perform specific calculations, like simulating the molecular structure of a new medicine, that would take a standard supercomputer thousands of years to complete. Yet the devices built to harness this processing power are arguably the most physically fragile mechanisms ever constructed. The slightest whisper of interference can destroy their work instantly. This extreme physical vulnerability is exactly why these machines are locked deep inside highly controlled laboratories, rather than sitting on our desks. Traditional computers run on bits, switches that are either a 0 or a 1, but quantum computers run on qubits. A qubit can exist in a state of superposition, meaning it holds the probabilities of being both 0 and 1 at the same time. That specific property is what gives quantum computers the massive processing potential. Maintaining that delicate state comes with a steep physical cost. Qubits demand absolute isolation from the outside world and extreme temperature control to function. To keep the physical qubits stable, they must be cooled down to around 10 to 15 millikelvins. That is negative 273 degrees Celsius, significantly colder than the vacuum of deep space. When you see photos of quantum computers, you usually see these massive, intricate golden chandeliers. But that entire structure isn't the computer itself. It is simply a highly specialized refrigerator built to protect a single microscopic chip located at the very bottom. The computational power of a qubit is entirely dependent on this space-grade cryogenic isolation chamber. The technology is permanently tied to massive, highly specialized infrastructure. All of this physical isolation is designed to protect the system against the primary enemy of quantum computing, a process called decoherence. Decoherence happens the exact moment a qubit interacts with the outside environment. When that interaction occurs, the delicate quantum state collapses, ruining the calculation. The triggers are absurdly minor. A footstep down the hall, a microscopic shift in temperature, a smartphone's invisible electromagnetic wave are enough to disrupt the system. Even a stray cosmic ray traveling from deep space can penetrate a laboratory, strike the chip, flip a qubit, and instantly ruin a complex calculation. The current state of quantum computing is a constant, desperate battle against the natural noise of the everyday universe. Because decoherence is so difficult to prevent, scientists cannot trust a single physical qubit to hold an answer. They break too easily. To get around this, engineers have to build a shield into the system itself, using a technique called quantum error correction. Researchers create a logical qubit, a single error-free information unit. The math is brutal. It takes thousands of physical qubits working together to maintain just one logical qubit. This creates a bottleneck. Today's best machines only possess around 1,000 physical qubits. When you apply the error correction math to current hardware, 1,000 physical qubits translates to almost 0 usable error-corrected logical qubits. To actually run the algorithms that make quantum computing useful, the industry needs systems containing millions of physical qubits. The delay in quantum computing isn't a software issue, it is a monumental hardware scaling challenge. We have to build machines large enough to simply outnumber their own microscopic errors. If a machine with millions of qubits is still years or decades away, it raises a logical question. Why are governments and banks panicking about quantum computing right now? The answer lies in an immediate cybersecurity threat known as harvest now, decrypt later. Bad actors are actively stealing and hoarding heavily encrypted data today. With current technology, they cannot read any of it. Their strategy is entirely based on patience. They are simply waiting for the day a sufficiently powerful quantum computer comes online so they can break the encryption retroactively. The mere fact that this machine will exist in the future is forcing tech giants and security agencies to roll out post-quantum cryptography today. The defense against quantum computers has to be built before the machines themselves are finished. Despite the hype, a quantum computer would be a terrible tool for running a spreadsheet or loading a web page. Unlike a general-purpose laptop, These are highly specialized machines designed for a very narrow set of mathematical tasks. Their true purpose is solving specific mathematical problems, optimizing complex global logistics networks, and natively simulating molecular structures for chemistry and medicine. We don't have quantum computers at home because they are not consumer electronics. They are industrial-scale scientific tools, built for problems traditional computers simply cannot comprehend. Quantum computing offers a revolutionary way to process information, but its greatest strengths, superposition and entanglement, are inherently its greatest physical weaknesses. We are not currently living in the age of quantum computing. We are in a global engineering race to build a physical shield strong enough to protect these fragile calculations from the universe itself. The goal isn't to build a better home PC. It is to construct a tool capable of simulating the most complex behaviors of the natural world.